Yeah, so let's start. So, am I audible? Yeah, okay. So, hello everyone. Welcome to this live session for NPTEL course on computer organization architecture. My name is Roja Mukherjee, and I'm a research scholar in the Department of Computer Science and Engineering, IIT Kharagpur. So, so we'll be solving some problems, sample problems like which are being asked in the assignments and also in the final exams. So the session is being recorded. You can find the video after the session. Also, this you can you can ask any question the in between the problems I will be solving. I will answer to them like at real time. So okay, let's start. So this is the first question. The question is which of the following statements is or are true? So option A is organizing memory in multiple levels may result in faster data access. Option B is um, we as we move from the processor, the speed of the memory increases. Option C, the by keeping the memory common keeping commonly used data in the memory that is near to the processor, memory access time may increase. So so uh, so mm, so if you so let's discuss each of the points one by one. So first, let's discuss option A. Option A says organizing the memory in multiple levels may result in faster data access. So this statement is true. If you have followed the lectures, you know that in a computer the memory are stored in layered way in multiple levels. So the first level is register, then cache, I mean L1 cache, then L2 cache, and then main memory. So as we have seen, the fastest among them is the register, then it is the cache, L1 cache, then L2 cache. So as we all know, if the data is present in the register, then the processor register is part of the memory that is actually present in the accessible to the processor. So this is the most fastest. Then we have cache. So if it is not present in the register, so we search the cache. If it is not present in L1 cache, we search the L2 cache, then in the main memory. So in a way, we have shown in the lecture that organization like this saves a lot of time and has a many fast access. So option A is true. Next, let's go to option B. It says as we move away from the processor, the speed of the memory increases. So this is actually false. Just wait a second, like something is not working for some reason. Yeah. So option B is false, and as it because as you shown in this figure, so the register that is the closest to the processor has a maximum speed to access. Then is the L1 cache, then is L2 cache, and then there is main memory. So now let's look at option C. In option C, it is that by keeping the commonly used data in the memory that is near to the processor, memory access time may increase. Actually, it is also false, because it is opposite. It basically decreases. So the correct answer is option C. So let's go to the next question. So the question is, consider a three-level memory hierarchy. Which of the following interfaces of the memory hierarchy are managed by the operating system? So option A is cache and cache magnetic disk. Option B is cache main memory. Option C main memory magnetic disk, and option D is none of the above. So cache and main memory are accessed by So the cache and main memory are accessed by are managed by hardware, and also main memory also the main memory and the magnetic disk are managed by the software. So if you notice, the options are A cache magnetic, B cache memory, option C memory magnetic, and option D main memory magnetic, and option D is none of the above. So the correct answer is C main memory and magnetic disks. That is or done by the that is basically done by operating system. Okay, so let's go to the correct option is C. So okay, so let's go to the next question, that is this one. So the question says, consider a machine with which takes 2 nanoseconds to fulfill a read request for cache hit and 45 nanoseconds to fulfill a read request for cache miss. If a program results in 90% of the cache hit, then the average read access time will be dash nanoseconds. Okay, so what is the average memory access time, like read access time formula? So average access time is like hit into t hit plus miss sorry 1 minus t8, that is the miss, to t miss. So here it is given. So here what is hit? So hit probability is here 90%. So h will be 0.9. And what is th? That is time for hit, like when there is a hit in the cache, that is 2 nanoseconds. So it will be 2 plus, what is the 1 minus h? So 1 minus h will be 1 minus 0.9 into what is the time miss, that is 45 nanosecond. So if we calculate this, it will be 1.8 plus 0.1 45, right? So it will be 1.8 plus 4.5, that will be 6.3 nanoseconds, right? So you have any questions regarding this? So what happens in a, what happens when like we use a cache? So either the data that we are fetching, that is either present in the cache or it is not present in the cache. So if it is present in the cache, that means it is a cache hit. So if it is a cache hit, there is a specific time that will be allocated for that purpose, for fulfilling the read request. So that is, in this case, is 2 nanoseconds. So so the average access time can be written as 0.9 into 2. 0.9 is the basically the time that is required for your the number of time, that is the cache is hit probability, that is 0.9 into 2, and another is uh, 45 nanoseconds, that is to fulfill a read request if there is a cache miss. So what happens when there is a cache miss? We need to fetch the data from the main memory. So what is the time required then? 45 nanoseconds. So this is the answer, 6.3 nanoseconds. So it is clear. Okay, so I will then go to the next question. This says that we have a two-level memory hierarchy consisting of a single level cache and a main memory. So we have a CPU, then we have cache, then we have main memory, right? So here it says that access time for cache memory is are 10 nanoseconds. So access time for here is 10 nanoseconds, and access time for main memory is 100 nanoseconds. Now also there is given that program is using cache 85% of the time. So this is used 85% of the time. So this will be naturally being used for the other percent. Now the question is, what is the speed up gain if you are using the cache? So this problem is solved using Amdahl's law. We have discussed in I guess probably in week 3, I guess. So using Amdahl's law, we will calculate the speed up. So the speed up is one divided by h by r. H is the heat time, that is 85% in this case, plus 1 minus h, that is the miss time, and the time when it is using the main memory. So what it will be, 1 divided by h is 0.85, r, what is r? 10 nanoseconds. So r is basically the rate of improvement. So what is the rate of improvement here? 100 divided by 10. So in main memory uses 100 nanoseconds and cache memory uses 10 nanoseconds. So the speed up basically is improvement is basically 10 times, right? So 10 times. So 0.8 divided by 10 plus 0.15. So if we calculate this, it will be 1 divided by 0. 0.085 plus 0.15. That is, if we calculate, it will be 4.25. Okay, so this is the speed up. So this is, we are using practically the Amdahl's law which we have discussed previously, right? So first we so the CPU directly either access cache or the main memory. So in this case, we have the cache access time is 10 nanoseconds and the main memory access time is 100 nanoseconds. So what is this? What is the improvement? It is basically 10 times, 100 divided by 10 times. So we will be using the Amdahl's law for this calculating the speed up. The speed up is 1 by h by r plus 1 minus h. H is the heat time of the cache and r is the improvement for cache, that is 10 times. 0.85 plus 0.15. So if we calculate, it comes down to be 4.25. So if you have any doubt, you can ask regarding this. So if you have understood this, if it is clear, then I will move to the next problem. Okay, so let's go to the next problem. So the question is, consider a main memory with 1024 blocks with block size of 32-bit each, and a cache memory which consists of 128 blocks. So if we use direct mapping, then where the block 128 and 256 will be mapped which block of to which blocks of cache memory. Okay, so what happens in direct mapping? So the question here given is there. This is the, suppose, cache, and this is the main memory. It says we have one, two, we have 128 blocks. So we have 128 blocks of cache, and what and the corresponding and corresponding 1024 blocks of main memory. So what is, so this is a direct mapping. So what happens in direct mapping? Blocks are arranged like for each, some group, for each group of blocks, a series of blocks in the main memory are assigned to a particular cache memory. So in this case there are 128 blocks of like cache memory. So it is said that where the blocks 128 and the 256 will be stored in which block of cache memory. The main memory blocks of 128 and 256, where it will be stored in the cache memory. So we know the cache memory starts from 0, 1, 2, and the last one is 120, 127, right? Similarly, main memory blocks are 1, 2, 3. The last one is 1, 0, 2, 3. So Since there are so 128 cache blocks, so what we will do is to place the block 128, we will do a modulus operation with the number of blocks. Number of blocks, and this is the block number. So what this will be? This will be 0. This will give 0. Similarly, 256 mod 128 also gives the value 0. So where these two blocks will be placed, the block number 128 and 256, that is 0th block position, that is this. So the answer is B. So if you have any doubt regarding this, you can ask. So basically the question says that where the block main memory block 128 to 56 will be mapped to. So we will just do a modulus operation with the number of blocks, and the answer will be the corresponding value. So number of blocks here is 128, and the blocks numbers which are to be mapped are 128 and 256. So it will be 0 in both cases. So let's go to the next problem. Okay, so the question is, consider a set associative cache that consists of 256 blocks divided into 16 block sets and a byte addressable main memory of size 128 kilobytes with block size of 32 bit each. How many bits will be there in the tag set and word field? So here are some terms we need to understand. So what is, first is set associative. This is one term. Then is there are 256 blocks in the cache. Set associative cache has 256 blocks. Next, each set has 12 blocks. Okay, so you need to process the question like this. So there is a set associative cache, and the total number of blocks are 256. How many blocks in each set? 16. And also it is a byte addressable. So what does byte addressable means? Each byte has a specific address. Each byte has a specific address that can be referred to it. What is the total memory size? 512 kbytes. And last one is block size of each each block size is size of each block is 32 bytes. So the question is, how many bytes will be there in the tag set and word fields respectively? So what is the how the set associative this is a address, memory address space. Right, so this is This is the tag field. This is the set identifier field, and the last is the offset. So in generally people call it as set offset, like not set offset, like it is sometimes people call it word offset, but like we should not always call it byte offset, word offset, because sometimes like this problem here it is a byte addressable memory. So why we call it a word offset that in that case. So let's jump into it one by one. So let's process it like this. Firstly, the caches 2 56 blocks. Okay. Now it says it is a set associative. So also it is says one set has 16 blocks. One set has 16 blocks. So how many sets are there? That is the first thing we need to find. Therefore, number of sets 256 divided by 60, 16, that is 2 to the power 4. So to identify each set we require 4 bit. So this one is 4. So the set field is 4-bit width. Next comes the offset. So here says the block size is 32 bits. Like in a block, there are 32 bits. One block, (32 bytes). And remember, this is a byte addressable memory, where each byte has a specific address. So we can write this as 2 to the power 5 bytes. So there are 2 to the power 5 bytes. So identify each of these bytes, we require 5-bit address, right? So this will be 5. Now the has a size of is 512 KB. So we can write that as 2 to the power 9 into 2 to the power of 10. So that is 2 to the power 19 bytes. So therefore in the memory there are 2 to the power 19 bytes. So to represent each byte we require then a total of 19 bits. Fine. Fine. So what will be the tag field? Is equal to 19 minus 4 plus 5, that is 10. So this will be 10. So the correct answer is option A. So any doubts regarding this? Or shall I repeat once again? Okay, so let's go to the next question then. This says a computer has 4 GB of 4 gigabyte of memory with 32-bit words, where the computer uses word level addressing. Each block of memory stores 64 words. The computer has a direct map cache of 128 blocks. How many bits will be there in the tag field? So again, let's go into it one by one. First is we have a 4 gigabyte of memory. Next is each word is 32-bit. Fine. Next is the computer uses a word level addressing. Previous one was byte level, this is word level. Here means each word, instead of each byte, each word has a specific address. Now it also says each block of memory has 64 words. Like, so each block has 64 words. Also, the computer has a direct map cache. This is not a said associative mapping. This is a direct map cache of 128 blocks. So, how many bits are there in the tag field? Okay. Again, let's go to it one by one. First is 1 word 32 bit. So we can write it as 4 byte, right? So the one word is 4 byte. Next, it says there are memory is 4 GB. So first one is how many, then how many there are words in the memory? So number of words for GB divided by 4 byte. So that is 1 G, that is 2 to the power of 30. So there are 2 to the power 30 words, and this is word addressable memory. So that means we have 2 to the power 30 words that has to be addressed. So I will come back to that. Okay, don't worry, Prasanna, I will come back to it. So there are 2 to the power of 30 number of words. So if this is the memory address, so here is the tag field, here is the cache index, so here is cache index, and here is the offset. Okay, so there are 2 to the power 30 number of words, and each we have to identify each word. So this total size will be 30 bits to identify each word in the memory, right? This is clear. Number of words is 2 to the power 30. So to represent each word we need 30 bits. Then let's come to this, then the rest of the part is easy, like less previous one. So there is offset. Offset is, so here it says each block, one block, 64 words, that is 2 to the power of 6. So in each block there are 64 words. So that means to represent each word uniquely in a block we need 6 bits. So this one will be 6 bits offset. Now cache index. So how many there are, how many the cache has, there is a cache of 128 block, 128 blocks cache, that is 2 to the power of 7. So to represent each block we require 7 bits, right? So this will be 7 bit. Therefore what will be the tag 1? 30 minus 7 minus 6 equals 17. So the correct answer is option B. Right? So if you have any doubt regarding this, so let me repeat once. So I will come to the next question again, like the previous question again. The question says we have one word, that is the question here says there are 6 gigabyte of memory, 6 gigabyte of memory, Also, each memory with 32-bit words. So each word is basically represents 32-bit. And the computer is at word level accessing. So in word level accessing, for each address, for each word, that is for each 32-bit, there is a specific address. Next, each block of memory stores 64 words. It says each block of memory has 64 words. Also, it has a direct mapped cache of 128 blocks. Okay, so let's do it one by one. One word is 32-bit, so that is 4 GB, and the memory is 4 byte. One word is 32-bit, that is 4 byte. Next, memory is 4 GB. Next, therefore, total number of words in the memory is 4 GB divided by 4 byte, that is 1 G, that is 2 to the power of 30. So number of words is 2 to the power of 30. Now it says, so so now if you look at the memory is word level accessing. So a total number of words is 2 to the power of 30. So to represent to represent each word at as an index, we need 30 bits. So the size of the address size is 30 bits. Fine. Let's we have shown that. Now it says there is one block has 64 words. Like, so in each block of memory there are 64 words. So to represent each word uniquely, we require then 6 bit of address. So therefore the offset is 6 bit. Fine. Next, it says there are 128 blocks of cache. What does 128 blocks of cache means? 2 to the power of 7 cache blocks. So to identify each block uniquely, you require 7 bits. 128 blocks is 2 to the power of 7, so it requires 7 bit. So what is the tag now? So total address length is 30 minus 7 the cache index minus offset 6. So that is 30 minus 7 minus 6 is equals to 17. So the correct answer is option B. This one is clear? Okay, so Prasanna, I will come to your problem again. In previous question, 19 bits are used to represent what? So if you look at the question, so this question says it is a byte addressable memory. So that means, unlike previous question where it was word addressable, each word has a particular address, here each byte of memory has a particular address. So that 19 is basically the total address size of each byte in the memory. That is what this 19 represents. And if you ask me how it comes, because it is given the size of the main memory is 512 KB. So that is 2 to the power of 19 bytes. To represent each byte, you require 19 bits. Okay, so these two questions I feel you should see simultaneously, because one gives an idea of a byte addressable main memory, and another gives a perspective of a word addressable main memory. So you will understand what does a word mean and what does a byte mean. So let's go to the next problem. So this says there is a n-way set associative memory. So n-way set associative we saw last question. What is a set associative memory? How like cache memory? So it says what will happen if we increase the value of n? Okay, so what does n represent? This is a very big confusion many faces. So n represent each set in a set associative memory has n blocks. Number of blocks in each set. So it says what will happen if we increase the value of n? Search time in option A is search time in cache increases. So option A is search time in cache increases. So this is true, right? So basically, if you have a previously a set in which there are suppose 4 blocks, so now if it increases to by 2 blocks, like it becomes 6 blocks in each set, then obviously the search space and the search time will increase. Right, so this is the problem. So search time will obviously increase if we increase the because previously you are searching in a array of 4 elements. Now you are searching in an array of 6 elements. So obviously if the value of n increases, the search time in cache increases. Now option B, freedom of mapping main memory block into the cache increases. Yeah, so now there is more number of places to play, like you have more space to accommodate each block in the memory. This is true because more space to accommodate each block. Previously you are only given 4, now you have 6. And option C is true. You can see, like, if we increase the value of n, the size of the set increases. If n becomes n plus 2, the number of sets block in the set increases. So all of them are true. Any question? Okay, so if you have any doubt regarding any question, you can ask, like from 1 to 8. So this was the last question. Basically these two questions are very important. Question number 6 or 7. Like this is a very common kind of questions that we will face not only in the exam. Also, if you are preparing for GATE, these questions are very common. Like what is the size of the tag? What is the size of the set? and what is the word field, how what will be the value. These are very primary questions, those are asked everywhere. Also this problem is also very important. This one, like what is the cache hit time. These are kind of the question you should prepare like more. So if you have any doubt, you can ask. So if you don't have any question, we will then end the session. So this was the last question. Um, so we will again meet next week in same time, 6 to 7. Thank you.